Verons i primaveres i els tarongers florixen perfecte.
Having said all this, we now move towards our final chapter, which is entitled Metacommunity Network Structure Determines Nonlinear Transitions in Biodiversity Resilience to Wildfire Disturbance. That is currently in preparation. So, we have said that disturbance have an impact according to species dispersal ability, that the temporal succession is also relevant in determining post-fire trends, but also that dispersal and the location in the network that you are also relevant in determining these colonization trends. So how we can join all this information in order to understand how our metacommunities will respond to the future incendiary that is being pictured these days. So how we can understand how the wildfire can affect the whole metacommunity region and how this network will respond to greater wildfire regimes. This brings us towards simulation models that can account with landscape relevance in determining metacommunity response, that of course they are simulation models, so they have limitations and assumptions that must be considered, but at the end they can bring or give useful insights to better understand metacommunity response after a disturbance. This means that we can change some of the characteristics such as extension or intensity and draw different future scenarios, taking into account all this information that we have defined. So in order to build our simulation model, we first have to reproduce our landscape. We have our water body network, and if we translate each one of these water bodies into a point in the landscape, we can generate a graph. Then each one of these points can be joined by different linkage distances, and therefore we can create several networks that can be linked or related with several or different dispersal capacities or landscape perceptions. So once we have created each one of these networks, for each one of these, it's time to create a fake metacommunity or a metacommunity that represents this landscape. So we have our local communities, each one of the points that we have commented, and their links that have been built according to the linkage distances that we have used. Then in each one of these local communities, we add 100 species having 10 individuals each. But these species will not interact between them. The only interaction that we will generate is the random death and birth and the colonization events that we will simulate. So we then randomly eliminate some organisms of each one of the local communities, and once we created this gap, we fill it through simulating colonization events between the connected local communities. If we repeat this procedure thousands and thousands of times, at the end we will be creating a fake metacommunity that will respond to the landscape structure that we have created. So once we have all our metacommunity, it's time to burn it. What we understand as a burned community is a completely destroyed local community with 0 species and 0 individuals, so the complete elimination of the whole community. To select the water bodies that were affected by the wildfire was easy. We can trace it with GIS programming, but then we wanted also to simulate different wildfire scenarios, taking into account the area, so the extension of this wildfire, and the intensity or homogeneity. What we understand for homogeneity is the percentage of water bodies affected within an area. So we have a determined area of wildfire, and this would represent a 5% intensity, this would represent a 50% intensity, and this would represent a 100% intensity, so the whole water bodies within this area would become affected. Once we have burned our ponds, it's time to recolonize them. So we simulate, using the same random approach, colonization events towards the burned communities and repeat this procedure several times, generating then a coalescent wave that brings all species into the burned ponds. So once we have done all this for each one of these networks that we have commented, we can then calculate some metrics in relation to burned ponds in order to obtain some results. These metrics are the mean richness after one iteration, so after the one colonization event after the wildfire, and also the mean richness after 100 iterations of the wildfire, so 100 colonization events after the wildfire. We can do this for the importable fire and for the fake fires scenarios. In relation to the importable fire, and remembering that our maximum species richness is 100, taking into account each of the networks that we generated having more disconnected landscape and more connected landscapes, we can observe the mean richness at T1, so one iteration after the wildfire. And what we can see here is that the species that perceive a more connected landscape, in only one iteration, they reach 100 species, so the maximum species level. But organisms perceiving a more disconnected landscape or having a more passive dispersal only reach the 40% of the available maximum richness. If time passes, so we simulate 100 colonization events after the wildfire, what we see is pretty similar values. Species that were at 100 are maintained at 100, of course, but organisms that were more affected practically present no change after 100 iteration events. This means that these organisms, due to their landscape perception that is really disconnected, are unable to reach the burned ponds, no matter the time that will pass. So now moving to the 400 simulated wildfires, we said that we created a gradient of areas, of intensities, sorry, and a gradient of areas. So we simulated a regional region of several scenarios representing different wildfires, being small wildfires with small intensity located here and great wildfires with great intensities located more or less here. This is interesting because we can locate our imported wildfire here and see how it is located within several future scenarios and how it will respond towards future scenarios. So we have our results in relation to mean richness after one colonization event and our results after 100 iterations, so colonization events after the wildfire, for each one of our landscape perceptions. The more disconnected organisms present a dominance of reddish-orangish colors, which imply practically zero mean richness after the wildfire. And interestingly, they don't change across time. This is what we have said. They perceive a disconnected landscape, and no matter the time, that their results are practically the same. Here, our wildfire is located in a yellowish-orangish area. Then, once we increase a little bit the linkage density, we already see blue colors, which imply practically 100% species after the wildfire, and also a change throughout time, becoming greater their mean richness in more connected landscapes. As we increase linkage density, the colors become bluer and bluer and bluer, and the change throughout time is still more clearer. Interestingly, our wildfire is always located in the blue, within the blue area, something that is informing us that is in a safety area in relation to the all drawn future scenarios. But what we see is that the change from a completely recovered community towards a completely compromised community is abrupt and nonlinear, and there is a tipping point where the metacommunity is unable to bring all the species into the burned ponds and therefore gets compromised. Interestingly, this tipping point is only driven by intensity, as we can see for the horizontal lines that present this graph. So is intensity the mainly driving force making or defining the metacommunity response after the colonizations? So if we try to sum up all this information, what we have seen is that for the imported wildfire, organisms perceiving a more disconnected landscape are the ones more affected and unable to recover, something that sounds us familiar. And also that in the case of simulated wildfires, homogeneity is the main driver of community change, and that this change from a completely recolonized community towards a completely uncolonized community is abrupt. In addition, that our wildfire is located in a currently resilient area, and also that the change in this area occurs between the 40 and 60% of burned ponds within an area. So from this point in advance, the community is unable to recolonize after one iteration or after 100 iterations. So having said that,